Okay, so in this thermodynamics question, we're given a little bit of information about what happens to a gas, and we're going to have to use our knowledge of some of the thermodynamic processes and gas law sorts of things to figure out sort of more about it. So the first part A is really, really straightforward. It's basically just checking, do you remember the sign conventions? So we want to find the change in internal energy. I'll just call this delta U. All right, so the change in internal energy, and we're told how much energy is added from heat and how much work is done on it. And so remember the thermodynamics law, first law, right? Q plus W. The important detail for this is the signs. So this, actually let's do it this way, right? So this Q is heat that is added to. That's when it's positive. If it's removed from, then it's negative. And this is the work done on. That's what makes it positive. And these are the same descriptions we have in the problem, so both our values are positive. So this is 3,200 plus 2,100 joules is 5,300 joules. So that's the change in internal energy of the gas. So now we need to talk and figure out what happens about the three things that describe a gas. Its volume, its pressure, and its temperature. So first, volume. For volume, we know something about how the work relates to volume. Right? Where this work is, again, the work done on the gas with that sign convention. So, since the work done on the gas is the negative pressure times the change in volume, for the work to be positive, we need another negative sign somewhere. Since the pressure can't be negative, that means delta V must be negative. Right? And if delta V is negative, that tells us V final is less than V initial, or it decreases. Right? That's the only way for positive work to be done on a gas, is for it to decrease in volume. So next, temperature. Temperature directly relates to internal energy, right? One more delta in there, right? From that equation. Right, that was the equation we used to relate a change in temperature to a change in energy. So if we are told this goes up, and the amount of gas is fixed, then our only conclusion must be that the temperature also goes up. Right? Okay. So finally, we're left with pressure. And we don't know any equations that directly relate to pressure, but we do know the ideal gas law. And we've already determined what happens to the volume and what happens to the temperature. And these are just constants. So, for this, we can rewrite as that. If the volume has gone down and the temperature has gone up, both of those changes make this whole side smaller. So therefore, to keep the whole thing constant, the pressure must go up, right? So our end result is that pressure increases, right? So it's a process of elimination one. Volume and temperature, we can directly relate to other equations. The pressure is sort of whatever it has to be to make everything else work out. All right, so on to part C. So now, instead of doing that, we're doing a simpler process. We're only doing 1,800 joules of work on the gas. So delta U is Q plus W still. But, so your first thought might be, well, this is, right, delta U equals W because we weren't told anything about the heat. However, we were not told that Q equals 0. All we were told is a certain amount of information about the work. So we can't do this approach. We have to use I'll be consistent, I guess, and we have to do that one. And here we are told in the text, right, constant temperature. So if temperature does not change, then delta U has to equal 0. Right? And this is how we answer part D. If delta U equals 0 and delta U equals Q plus W, then W has to equal negative W has to equal Q. And so Q must equal negative 1800 joules. That means energy has to be transferred out of the gas as heat. Right? And so that's the answer to that one.